during the talk. So today, what I plan to talk to you about is the distribution of entanglement. So you've seen so far some proposals on how to do quantum networks, different technologies using continuous variables or discrete variables with the prepare and measure or entanglement-based protocols. And today, what I'm going to detail is my plan on distributing entanglement for entanglement-based quantum communication. So just before I delve into the problem itself, unlike my former colleagues, I might be unknown to you. So I'm Rafael Barros. I have been recently hired at the University of São Paulo. And just so you know a little bit of my background, I came from Zella's lab, where I did my work on optical parametric oscillators with structured light. So my background is a lot on structured light. After that, okay. Is it me? Okay, no, I can close this. After that, I went to Finland to do a postdoc there, again with structured light, but now in the discrete variables regime, in quantum optics experiment with a focus on quantum frequency conversion, which is something that I'm going to mention later in the talk. So after that, in late 2024, so December 2024, I came back to Brazil to start my own laboratory at the University of São Paulo. And this is the Quantum Structured Light Laboratory at the Physics Institute. So in that institute, our focus is on a few of these things. So we are working on building entanglement sources, also on distributing entanglement, as I'm going to mention here, on doing quantum frequency conversion. I will detail what this is later on, and on the spatial-temporal manipulation of light for different purposes, be it for the preparation and manipulation of entanglement or for classical optics experiments, which is something, which is a topic that is very dear to me. So this laboratory is being funded by FAPESP. We had the luck to get funding in the QT, the Quantum Technologies Initiative of FAPESP approved in the Young Researcher Grant. So we got roughly $1 million 2024 dollars. It's important to specify that it has changed since then. And so it's definitely not enough to go to the moon alone, but we have enough funding to start a lab and to do a lot of good work. And that's what we started doing. So I'm going to mention a little bit about these three topics. I will leave the spatial temporal manipulation out of this talk, maybe for another occasion. So okay, so first of all, I will focus here a little bit on the students. So it might be a little bit redundant if you are very familiar already with the concepts of entanglement-based quantum communication. So I will just start from scratch. So what exactly is entanglement-based quantum communication? So entanglement, when we refer to that, we have basically a source of entangled photons. I will show one example of this source of entangled photons soon. And this source of entangled photons produces pairs of photons. They are created together, okay? So they're created together and they go through a channel that is composed of either fibers or free space and fibers or water, whatever, okay? So these photons, they go through these channels and they go to remote parties, A and B, often referred to as Alice and Bob, where these photons will be measured. And the information is encoded in these photons in different ways. The maybe most well-known way is in the polarization. So you have bits of information, or quantum bits of information, that can be encoded in the two-dimensional subspace that is spanned by the polarization vectors. So you can have horizontal polarization, vertical polarization, or its complex superpositions, right? So with this, you can essentially create an entangled state using the polarization degree of freedom. You can create an entangled state like this one, where you have here in this state vector, you have the first slot corresponding to the photon that goes to A, and the second slot to the photon that goes to B. So you can have, this state is a superposition, a coherent superposition of both photons being horizontal and both photons being in the vertical. So just to get to know what exactly that means, I will make a very visual and simple simulation of an entanglement-based communication here. So let's assume first that you have this state that is, wait, just a second, is this my mouse? No, this one. So let's just assume that you first send these photons to Alice and Bob, but you don't measure what is going on with Bob. You just measure for Alice. And then what I want to know is, well, Alice has some detectors, and she can detect on the computational basis, so she can detect either horizontal or vertical, but she can also detect in the plus minus 45 degrees and in a sort of multiplexed scheme. So there is one detector for each possible outcome. These are projective outcomes, right? So if Alice measures a state like this, what she will get is something like that. It's a random sequence of bits that is corresponding to which detector is clicking. So I'll just come back to this. So there's the information of which detector is clicking in this case is completely random. So Alice ends up with a completely random bit string, and this is a consequence of the fact that if you have an entangled state to begin with, then the state, the reduced density matrix of one of the parties is a complete mixture. So for Alice, this single photon is completely indistinguishable from a photon from the sun, for example. It's a completely unpolarized light field. And of course, the same will happen with Bob. Bob will also get a completely random bit string. But what is interesting is, well, because of the correlations that they have, if Alice and Bob measure together, they will end up with completely random bit strings, but these bit strings are identical. And this is exactly the nice thing about this, about entanglement here, because you have randomness in each of the parties, but these random bit strings, they are identical. So you can build a cryptographic key with them. And, well, so far, everything okay until here. I mean, you have an entangled source, and you send these photons away, and then now you have means to generate identical bit strings to make the one-time pattern encryption, right? So you need these keys to be completely random and to be completely identical. Of course, this is a representation of an ideal scenario where you don't have any bit error rate, for example, right? So the correlation is perfect. But of course, the experimental scenarios are a little bit different from that. But the message here, the security of this protocol or this mechanism is exactly based on entanglement. So if a possible eavesdropper tries to intercept the communication here, this approach is bound to fail because there is no information until the photons are measured. This is what Eckert mentioned in his own paper in 91. He said that, well, the information doesn't exist until the photons are measured. This is when the information comes into being through the correlations of the measurements. So if the eavesdropper can try to intercept and resend or do other types of coherent attacks, but it has been shown that entanglement-based quantum communication is secure, provided that you keep your experiment under a given amount of error rate. Okay, so my focus in this talk would be to basically separate the entanglement-based quantum communication scheme in three parts. So the detection, the distribution, and the generation of entanglement. And especially the first and the last, the detection and the generation. And each of these parts of the protocol encompasses a series of technical challenges that we are all trying to deal with in Brazil, basically. So the channel, for example, the channel is something that is classical. It's a fiber, for example. It can be a free space channel. And this is something that we all have the same problems with. So if you build a channel, if you characterize a channel, you can use different protocols for quantum communication. So I'll start from that. But you can also have, for entanglement-based quantum communication, based on single photons, you have the problem of the detection of single photons, right? You have to propagate the single photons in a wavelength where they don't attenuate so much. And this is the case for telecommunications, as we heard before. So if you work at 1550 nanometers, that's good for propagation in fibers, but unfortunately, it's not that good for detection. So you need very expensive equipment to detect, although the propagation is very easy. So there's some trade-off in which wavelength you're using here, and also the detector technologies, the detection technology is also affecting the maximum secure key rate that you can achieve, as I will mention a little bit later. And on the entanglement photon, entangled pair source, or entanglement photon source, We have also a few technical challenges here. For example, of course, we want the source to be as bright as possible. And this oftentimes involves some engineering of the source and the coupling efficiencies and which crystal you're using, but also the bandwidth, right? Because this photon source, it has to be bright, but also it has to be spectrally bright, so you can use multiplexing schemes to increase the number of users in your network. And these are a few of the challenges that we are trying to deal with this project. So I will start by detailing the channel that we are planning to use, and then I will move to how we are planning to use it. So the channel that we have at hand is this one. So we like one of the channels. So luckily, the University of São Paulo has some network of dark fibers that we can use for quantum communication. It's called the backbone IFUSP network. And a few of these links are detailed here. So this is a part of the state of São Paulo. And these are different campuses of the university. So you have one in Piracicaba, one at São Carlos, and one at Ribeirão Preto. And there are many pairs of dark fibers connecting these universities, and we were provided a pair of these dark fibers connecting exactly these three campuses. So this is the fiber link that we are going to explore in our, let's say, long-term goal. Towards the end of the project, we want to be able to distribute entanglement in this fiber link here. So just to have an idea of the complexity of this, well, this entanglement distribution scheme, these cities are very far away. São Paulo is very big. So what we have here is that we want to do is to install an entanglement photon source at São Carlos, and to send these photons to Ribeirão Preto and Piracicaba. And these cities are, for example, São Carlos and Ribeirão Preto. The fiber between them is approximately 100 kilometers long, and between São Carlos and Piracicaba we have 140 kilometers, and that introduces a lot of attenuation, so it's not all sources of photons, it's not all wavelengths that you can use with current detector technology. So for example, we have the characterization of these fibers already, and what we have is that the transmission of the fiber, and here, of course, I'm considering the transmission of 2 photons, which is something that increases the complexity. You have to multiply the transmissions if you want to detect, to calculate what is the pair rate that you have. So the transmission of the photon pair at 1310 nanometers, which is an interesting wavelength for quantum communication, is on the order of 10 to the minus 9. So it's almost completely impossible to do quantum communication at this wavelength in networks of this size. However, at 1550 nanometers, it's still okay. We have something like 10 to the minus 6 for both of the photons, but mega pairs per second is not something very difficult to achieve in the lab. Actually, like, there has been some advances towards gigapairs per second, and that's something that we are also trying to implement in the lab. So in this network, what we are going to do is to focus on the 1550 nanometers. So installing here an entangled photon source with photons at 1550 nanometers, and to send these photons away. So first, what we want to do is to put here a source of polarization entangled photons, but I will mention also some alternative technologies later on. However, of course, this fiber network that I showed is a long-term goal, because it's a very challenging project, and we're not going to test our equipment, to test our sources already in such a difficult scenario. So what we can do here is to use another network of dark fibers belonging to the University of São Paulo. And when I say belonging, this is very important. Of course, there are many different networks that we could use in principle, but these networks, they don't belong to the universities. They belong to some network provider, and you have to rent the fibers from them, and it's not that easy. You don't have 24/7 access to the fibers. So having that at the university, having this kind of infrastructure at the university, it's very important. So luckily, again, we have another network of dark fibers in the São Paulo campus, in the Butantã campus. So I didn't draw it here, but there is a fiber network that is surrounding the campus, in many loops, essentially. We have around 100 loops of dark fibers that we can assess individually in 5-kilometer steps. And we are, well, it was a nice surprise to know that one outlet of this ring network comes right inside the laboratory. We have a rack there from the Information Authority, STI, from the university, and we can use it straight away in our experiment. That simplifies a lot of things. So this is the network that we are going to test our equipment on. So just as an estimate, instead of the 40 dB and for 1310 and 30 dB, for example, for 1550, in the other network we have something like 0.22 dBs per kilometer. So if you have 5 kilometers, you're still like in a very good attenuation. So that's what we're going to try first. And so these are our channels, as I mentioned. So now, what about our sources? So when we talk about entangled photon sources, we are thinking about parametric down conversion. So how does that work? Parametric down conversion refers to the generation of pairs by pumping a nonlinear crystal with a laser beam. So you have here, for example, this blue laser beam. Let's say it's 400 nanometers. You pump a nonlinear crystal, and this nonlinear crystal will annihilate the photons from the pump and will generate pairs. And because this process is parametric, which means that the crystal is left unchanged after the interaction, some quantities have to be conserved. So the energy has to be conserved, for example, but not only. You have to conserve also the linear momentum and the angular momentum as well, something that I didn't mention here, but that gives rise to a plethora of interesting experiments that you can do by playing with the correlations of these photons. But in our case, the most interesting correlation here is that these photons are generated at the same time. So you can play with these sources in such a way that you generate entangled states by, for example, having two crystals, so one that generate photons in the horizontal polarization, and the other one that generates photons in the vertical polarization. So if you can make these two crystals to generate photons coherently, for example, if you stack them one against the other, then that's already sufficient to generate photons that are entangled in polarization. So this is one example of a recent article from 2022 using a Sagnac type polarization entanglement source, and that pushes towards the limit of gigabit per second rate for QKD. Not for the protocol, but for the generation. So when I mean like gigabit per second, I mean gigabit per second at the source, like not taking into account the attenuation. Of course, if you take the attenuation into account, you have to recalculate what would be your maximum bit rate. And as Valeria said in the beginning, if you have like 100 kilometers of fiber, then you go down to roughly kilobit per second. But it's important to mention that when we talk about quantum key distribution, we are not talking about direct communication. So if you have kilobit per second, that's still useful in a sense because you can accumulate these keys over time, and when you need them, you can use them. And of course, we expect the QKD to be used for critical infrastructure and not for like daily communication. What we expect for the future is that most of the communication will still be classical or post-quantum, but when it's actually critical that cannot be hacked in any way, then the QKD might come in handy. So this is an inspiration for entanglement-based QKD based on polarization. There's this article from 2020 that is relatively recent that implements actually a 8-user network with a single pair source. So this is the source. It's a Sagnac loop with a lithium niobate crystal. We're getting a few of those. We have now a list of lithium niobate crystals to play with and lithium niobate waveguides as well. And with a single source, because of the broadband aspect of the source, then you can send these frequencies, the different parts of the spectrum that are detailed here for different users, and provided that these users are able to measure these photons at different wavelengths, then you can build a fully connected network. So every user is connected to every user through a single photon pair source. So this is a good inspiration for this work, but of course there is a big challenge here that well, I want to call your attention to, that although you use only one source of entangled pairs, you have to have detectors for each and every user in the network. And that adds a lot to the cost. And when we're talking about network, we're talking about something that is applied. We want to make it maybe a business out of it. And cost is something very important. So just keep that in mind for later on. Another technology, another mechanism that you can use to generate entanglement is by playing with the temporal correlations of the photons. So this is one example. You can generate a pulse from a laser, for example, a short pulse, and then using a simple interferometer, with different lengths in the two arms, you can create two copies of the same pulse, one that is called like short, early, and the other one that is late, or short and long, referring to the paths that the pulse takes in this interferometer. And because the chance that the pairs are created in this nonlinear crystal are very low, then the state that comes out of it can be written in this way. So it just means that either the two photons are generated by the short pulse, by the pulse that went through the short length of fiber, or they are generated both by the pulse that went through the long length of fiber, but never both, because this probability would be very low. And this is an entangled state that you can use just as you would for polarization entanglement, and it has that added advantage that, well, if you're using polarization, then when you send these photons away, you send them through fibers, and fibers change the polarization of the photons. So as Ella was mentioning, if you're using free space, then maybe you can play, we can play with the spatial structure, and you can use this vector beams to not align the sources, the detectors if you need. So you have the Alice and Bob detectors, and you have to align their bases, right? So if you're in free space, maybe you can play a trick not to have to do this. But when you're doing it in fiber, that's something that you cannot get rid of. So essentially, what you need to do is to develop or to buy expensive equipment to correct for polarization changes very quickly, and that adds to the complexity, especially if you think that you have many users in the network. In contrast, in this case, you don't need to care about the polarization. What you need to care about is about the length, the fiber length in this interferometer arms. But these two, they can be controlled with temperature, which is something much cheaper and much easier than the control of the polarization with this fast polarization modulators. So it's much cheaper and much easier. The problem here is that because you're playing with time now, the time of arrival of the photons becomes important. So you have to care about the jitter of the detectors and about the dispersion effects. So this is one reason why the sources that I mentioned that we are working on, we are working in the wavelength of 1310 nanometers in the O band. And one of the reasons is, of course, the dispersion. So if you work with 1550 nanometers, you have dispersion, you have to get rid of it. One way to do this is to add more fiber, but a dispersion compensating fiber. But that adds losses as well to your system. Another way is to use 1310. You have more attenuation, but for networks that are not extremely long, that might come in handy. So that's what we are doing. There's virtually no O-band sources in the market that you can just buy. So there is still some unexplored area there that we can attack. So that's what we are going for. And just as an inspiration for that, for this time-being entanglement, there's this very recent work from 2023. So this is a network of 50 kilometers of fiber in the southern coast of France that is using just a laser and a lithium niobate waveguide to generate the photons. And the key rate in this network is there, for example, in the 6 kilobits per second, which is a very interesting benchmark that we might want to achieve in our networks. All right, so just, so I've shown here some of the advantages or some nice aspects of using entanglement for quantum communications, but I have only mentioned so far SPDC, or parametric down conversion, as a source of these entangled photons. And of course, SPDC has limitations. And it comes from the fact that when I say that this pump is generating pairs of photons, it's not very much true. So these photons of the pump, they are being annihilated, and if you annihilate one, then you generate one pair. If you annihilate two, then you generate two pairs, and that becomes a problem. Because then if you generate two pairs at the same time, and you have some attenuation in your network, it might be that you lose one photon from the first pair and one photon from the second pair. So you generate, you measure a coincidence between photons that are not correlated at all. So you can generate more photons if you pump harder, but as you increase the pumping rate, you also increase you decrease the quality of the entanglement that you measure. So there is a trade-off between these two factors, and this is illustrated in this also recent work that studies what is the effect of the source statistics. So what is the limit, the fundamental limit that you can achieve with parametric down conversion? So there is a limit of essentially of how many key bits that you can get securely per window of the detection. And I'm referring to that because for SPDC sources that are pumped with CW light, with continuous wave light, it's not very important what is the pump power alone. You have to take into account the pump power and the detection window. So what the quantity that is bounded is the number of detections per window. So you can increase the count rate by making these windows shorter and shorter and shorter, and that's something that is not under the control of the source maker, and instead it boils down to the detection technology. So that's why it's important to make detectors that are faster and faster. Now currently you can buy detectors that have a resolution of 20 picoseconds, for example, but they're very extremely expensive. So that's a problem for SPDC. So this here is showing that for different attenuations, you have this R key here is the secure key rate per detection window, and you see that the maximum value here is around 0.029 when you have 100% transmission, but as you increase the losses, then this value just goes lower and lower. And of course, this is a modest estimation, so it's just a lower bound for the key rate, but still it shows the kind of limit that we have. And there are other types of sources. I don't work with them, but I know there's people in Brazil that are working with them. This like quantum dot sources, for example, and the quantum dot sources, they are not limited by the same mechanisms. All right, so I've talked about both the distribution and the generation of these photons. So now I will finish up with the detection, which is something that I find extremely interesting. So just to summarize, you have different ways to detect these photon pairs. So if you're working with telecommunication wavelengths, for example, the best detectors that are in the market are the superconducting nanowire detectors. So they are very good. So they're very efficient. You can get like 80 to 85% efficiency in the, let's say, in the base model of these detectors, and you can go up to 90, 95 if you throw money at the problem. But the problem is exactly that these detectors are too expensive. So we're getting some of those for the lab, but just for as an idea of the order of magnitude, if you want one detector in your lab with like 4 inputs or 6 inputs, you have to pay something like 150,000 euros. And of course, if you think of a network like the one I showed before, with 8 users all connected to each other, it's completely, like, this is not gonna happen, at least not in Brazil. And if it happens in other countries, it's gonna be for proof of principle. It's not going to become like a business model if you have to pay that much for the detection. On the other hand, you have these avalanche photodiode detectors that are relatively inexpensive. So for example, one of those costs around 6,000 euros. Okay, but and it's very good actually for visible light and for near infrared. If you're using 780 nanometers, it still works fine. But it doesn't work for telecom. So you cannot be used for fiber-based networks that are very long. If you have short fibers, as Danielle was mentioning, then you have then you can still use the fibers for 780, for example, or 850, but well, for long fibers, the attenuation is just too long. You have to move to telecom, and these detectors don't work anymore. So the question is, like, is there a way to use these detectors that are very much available, not too expensive, you don't need cryo, it's just plug and play. Is there a way to use them for telecom? And the answer is yes. There is a process that is called quantum frequency conversion, and it works as follows. So you have these input photons, so let's assume that these photons are telecommunication photons. This omega-1 can be 1550 nanometers. And you have a very powerful laser field that we call the dry field that interacts with these photons in a nonlinear crystal. So the process that will take place here is the sum frequency generation process for those that are acquainted with nonlinear optics. So essentially, these two fields will sum their frequencies. You're going to annihilate one photon from the input photon. You're going to annihilate the input photon and one photon from the dry field. And with that, you're going to generate one photon at the sum frequencies. You have omega-1 and omega-2. You end up with omega-3, which equals omega-1 plus omega-2. And at this process, what is interesting is that this process is described by a Hamiltonian of this form. And for those that are not like from the field, this means essentially that the quantum dynamics of the frequency conversion is a beam splitting dynamics. And the splitting ratio of these dynamics is controlled by this parameter kappa here, which is proportional to the power of the dry field. So by changing the power of the dry field, you can make this process as efficient as you want, of course, limited by the phase matching conditions and inherent losses of your device. But for example, you can make it with near unit efficiency and even see Rabi oscillations if you increase too much the power. And actually, this is something that has been used in one of the most successful QKD implementations in the world, which is in the QKD network in China. So what they did is that for short fibers, for short links, they used this indium, gallium arsenide APDs, which are very problematic for QKD networks. They have low efficiency, super high dark count rates, and after pulsing effects. But for the longer links, what they did is to use these up conversion detectors. So what they do is to have, they have like 1550 nanometer photons and a 1950 laser beam, which is not so easy to get, but still. And they do the up conversion in a lithium niobate waveguide. And with that, they get very good conversion efficiencies. I don't remember exactly what the conversion efficiency is in this case. But what is important here is that if you take into account both the conversion efficiency and the detection efficiency in the APD, you have a detection that is better than the APDs for 1550 and a dark count rate that is better than the APDs for 1550. So it is a viable technology, and it's not even optimal because this lithium niobate waveguides, although very efficient, they have losses that are linear losses, and they don't come from the nonlinear process. And this is why, in our case, what we want to do is to go for cavity enhanced quantum frequency conversion, because if you're doing the process in an optical cavity, in a bulk optical cavity, then you're not bounded by the losses, by the coupling losses in a waveguide. So this is the kind of thing that we want to do. This is one example of an experiment that is actually very old, from 2004, 20 years ago. And what you have here is a conversion efficiency, external conversion efficiency that is very close to 100%. So with that, you can get much better than the current APD technology for 1550, spending hopefully a fraction of the money. And that might be an interesting solution if you want to build a network with many users. So with that, so these are the things that we have been working on. So essentially, our idea is to develop these sources and to develop this up conversion detectors in the lab and to implement them in this channel that I mentioned to you. And of course, especially just like going one slide back here, of course, this kind of up conversion technology is interesting not only for QKD, but for example, Danielle was mentioning that if you want to interact with a quantum memory, then 1550 is not that good. But it doesn't mean that you have to propagate the photons at 780. You might want to propagate the photons at 1550 and then convert them when you need to interact with some device. The same thing for NV centers is not something new, but this allows you to bridge the gap between different ranges of the electromagnetic spectrum. So just in summary, we have been constructing now with the equipment that's just arriving a new lab where we're going to work with sources and detectors for quantum light. And well, we have the goal of distributing entanglement across the state of São Paulo in a network that has not been explored yet. And we are very open to collaborations with different partners, and some of these build a network that already works nowadays. So there is Zella in the Quantum Rio network, in the LMCAL at the University of São Paulo. The acronym is a little bit long, but it's Laboratory for the Coherent Manipulation of Atoms and Light. There is Felipe Barbosa at Unicamp. We have been talking about different ways of using lithium iobate for quantum frequency conversion. He has been doing the periodic polling and everything in there. So we have collaborators at the Aeronautic Technological Institute, ITA, also at Cimatec with Brian. We have been talking about free space communication with adaptive optics. Breno Marques at UFABC, we have been talking since the beginning of the project. It's listed twice here, it was an accident, sorry. And there is Cristiano de Matos in the Mackenzie Institute. We have been also discussing how to use different materials and not only bulk Chi2 crystals for quantum frequency conversion. And with that, I close, and thank you very much for your attention. And if you want to contact me, just read this QR code. And that's it. Thank you very much.
Thank you, Felipe. So we have time for questions. Unless everybody is hungry and eager for pizza, or...
There's one over there.
Okay.
Hello, thanks for the talk. It might sound naive, but just a little question. I might have missed something. Do you get perfect phase matching, or do you use PP crystals?
We are aiming at PP crystals. I mean, with lithium niobate, you need PP crystals if you want to achieve the type 0 phase matching, which is by far the most efficient one. Yeah. There's different ways to tune the phase matching. There is a student here, Lucas, that has been working on that, on using structured light to tune the phase matching without periodic polling. Okay. But that's still something under development.
Okay, thank you.
Any other questions?
Hi, thanks for the nice talk. I'm just curious, actually, in one of your last slides, you've shown the upconversion efficiency can go above 80%, but yeah, it's something like 20 watts of circulating pump power. Mm-hmm. So do they need a special crystal with a high damage threshold for this, or is...
no, I mean, this one is just like a magnesium-doped lithium niobate, doesn't seem to be a problem. Lithium niobate does have the problem of the photorefractive effect, but if the optical cavity is not a standing wave cavity, this is not a problem.
Okay.
Yeah, it's not the damage. The damage is not the problem here. It's just, but the photorefractive effect is a problem. Yeah, but if the cavity is like this bow tie type of cavity, it's no big deal. Yeah.
Okay, thanks.
Okay, so if you don't have any questions, you can take the time for the lunch and post the session to bring them back in the round table. So thanks, Rafael.
Yeah, thank you.
And we can merge now poster session and lunch together. We'll be